Hello, welcome to a new video. And this video is on topological spaces. We will see the definition of topological spaces, and we will discuss some examples. Then we will go through some simple theorems. To define a topological space, first we require a non-empty set. We name this non-empty set capital X. So let X be a non-empty set, and we then from this non-empty set we make a family of subsets. So it is possible to find or to find different subsets of the non-empty set. So the smallest subset is the null set, and the biggest one is the whole set, the actual set, capital X itself. Okay, then between these two limits, then the empty set, between the limits of empty set and the whole set, there exists different subsets of varying sizes. So you can consider any of these subsets. Any of these subsets can be included in the in the family. In this can be called the family of subsets. So in this family of subsets we can include any subset of X, and we after taking such a family, we then proceed to check whether three conditions are satisfied by the family which is defined, which is taken here. So next that means we now verify whether three conditions are satisfied by the members of this family. The first condition is whether the null set and the whole set both are present in the family. See, this is called this family is called tau, and this is pronounced as tau. So whether phi and X both belong to the tau, belong to the family, that's the first condition. You can very easily verify that. The second condition which is to be verified, whether the union of any members of tau, members of the family, union of any member, see, each member is a subset of X. So whether the union of any members of any number of members of tau is also a member of the same family, of the member of tau. So whether any union of we can call that union any union of whether any union of any number of any union means any number of union of any number of members of tau, whether it is also a member of tau. If it is okay, then we can proceed to check the last condition, whether the intersection of only a finitely many number of members of whether the intersection of any finitely many members of the family tau is also a member of the same family. Okay, and if this is also satisfied, but you know what is the problem with taking the intersection of any family instead of any finitely many member? So if you take intersection of any or infinitely many number of members of tau, then that may give us a situation, that may lead to a situation that the answer obtained, see, the intersection is the answer obtained may not belong to the family. So this situation may happen. Okay, so that some examples are there, simple examples are there. That example will be discussed in another video. Okay, and these are the three conditions that must be satisfied by the family tau, in order to be that family called a topology. See, if these three conditions are satisfied, we say that tau is a topology. Tau is a topology defined on the non-empty set. and after getting a topology tau, we can together you can call that X, and together with the topology, it's X and tau, X and tau together make a topological space. See, the tau makes this space X, the non-empty set X, a topological space. Hence we can say that X comma tau is a topological space, or there exists a topological space, or X has a topology. We can say it in different ways. See, we can say that, simply say that X has a topology tau. But one important thing is that there can exist different topologies. See, depending upon the variations in the variations in the subsets that we actually select to include in the family. See, if the members included in the family varies, then depending upon that variation, and this tau also, that family will also change. Therefore, we get different topologies on the same set. We get different topologies. So you can name these topologies: first topology, second topology, like tau 1, tau 2, the third topology, tau 3, etc. And these names can be used. Okay. And then one another thing, see, another important thing is that in the case of topological spaces, we say that a subset of X is an open set only when it belongs to the topology which is defined there. See, we can say that whether a set is open or not, whether it is open or not, only depending upon the topology which is defined there. Therefore, some subset of X, a subset of X which is present in a topology, based on that you can say that it's an open set there, but it may not be present in another topology, in a different topology. It may not, that's the same set subset may not be present there in a different topology. Then we cannot say that it is an open set there. Therefore, in that based on that the second topology, based on a different topology, that subset may not be open. So it's a very important thing that you should keep in mind. Okay. Then and therefore, see, thus we can say that members of tau, therefore and this situation therefore leads us to call the members of the topology, see, or members of topology as open sets. So all the members of the topology, which is underlying topology here, which determines the topology or which makes the space X a topological space, we can call that all those subsets are, all those sets are open sets. Thus we can we can restate that the three axioms. So see, we can see that we can call these statements as axioms of the topological spaces. So we can restate the axioms of the topological spaces including or incorporating the term open instead of the member, instead of the word, or instead of just saying that a subset is a member of tau, you can say that it's open. See, the members are open. Therefore, the statement can be like this. See, the first one is both X and, see, this is capital X actually, and so correct it. This is not small x. This whole space capital X and phi are open sets. Capital X and phi are open sets. Here the open sets stands for is a member of tau. See, so whenever one subset is a member of tau, then we say that it is open. So that word or that usage is a member of tau can be replaced by the another usage is an open set, So both X and phi are open sets, and union of any family. See, union of any family of open sets. Union of any family of open sets is an open set, and intersection of any finite family of any finite family of open sets is an open set. See, see, that's why it's called a finite intersection. Finite intersection of open set is open. So here that word is missing. Intersection of any finite, that word should also be used. That's important. Any finite family of open set is open. Now we can see some examples. See, the usual metric, you have studied the usual metric defined on the real line. We consider the real line as x equal to r. Then we have the usual metric defined on r, and that is modulus of, if x and y are two, small x and small y are two members of r, then modulus of x minus y is the distance between the 2 points, and that gives us a metric, and that metric determines open sets. By taking all those open sets, by considering the collection of all the open sets determined by this by that usual metric, can make the space R a topological space. Thus that topology, is called, the corresponding topology is called the usual topology, which is defined on R. We say that it's the usual topology. So it is the topology generated by the usual metric on R. Next we consider, as the second example, we can consider the topological the space. See, X is equal to Rn. That is the nth Euclidean space, n dimension Euclidean space. And here also we have that usual topology, usual metric. Using that usual metric which is defined on Rn, and that can determine open sets, that can define open sets, and these open by taking the collection of all those open sets, we can make a topology, and that topology can be called the usual topology on Rn. Next example, third one, here we see a special kind of topology. In the next few examples, we are going to see some special kind of topologies. So let X be a non-empty set. A topology generated by the discrete metric is called the discrete topology. See, we have the discrete metric defined on X. That discrete metric is a discrete metric. Suppose D is the discrete metric, then D of x y equal to 1 if only if x is not equal to y, and equal to 0 if x equal to y. So D of x y equal to 0 if x equal to y. That is called the discrete metric. And then with respect to the discrete metric, in this discrete the discrete metric can determine a topology, that is called the discrete topology. So see, in this topology, the discrete topology, in the discrete topology, every subset of X is open. So here it has the property that every subset, see, in you consider every subset of any subset of X, then it is open. Every subset of X is open with respect to the discrete topology. So fourth example, this is the trivial topology. Here we consider for any non-empty set that in the topology we consider only two subsets of phi, the empty set and the whole set X, and then it can satisfy all the three axioms. So it can be called it can be a topology, and this topology is called the trivial topology, but it's of very little interest to a student of general topology. So you see, we are now going to define another important topology. It is called the finite complement topology. See, finite complement topology. How do we define this topology? Let's see that. See, consider a subset. Consider a set X with the topology tau prime, tau dash is defined on X. X is a non-empty set, and tau dash is a topology consisting, and this topology consists of it consists of the empty set phi and the set O and the subsets of X. See, it contains empty set. First of all, it contains empty set. The topology tau prime contains empty set first, and also it contains all subsets of X. That subset is called O. An arbitrary subset O of X is member of tau prime, but there's a condition for this set to be satisfied to become a member, and that condition is that x minus o, that is the removed set. When o is removed from x, or it can be called complement, then complement of o, or complement, that is x minus o, if this set is a finite set. If x minus o is always finite, then that can be included in tau. But suppose it is infinite, then it cannot be. Suppose o's complement or complement is infinite, then it cannot be included. It is not included in tau prime. That's also important. So note that. After that, after defining that, the family of non-empty subsets, family of this subset can you can show that it can make a topology. It can determine a topology on X, and this topology is called the finite complement topology, because we are taking complement of members of tau. We are taking complement of members of tau, and then we check whether it is finite. Whether the complement of members of tau, is finite, then only we proceed. See, remember, for a subset of X to become a member of the topology, the condition that its complement must be finite is satisfied. That is why this topology is called the finite complement topology. The topology, this topology is of interest only when X is when X is an infinite set. Therefore, see, one important thing is that, and such a topology can be defined. This kind of topology can be defined only when capital X is the whole set X is an infinite set. See, when it is a finite set, then this definition does not work, so it is meaningless. So if X is an infinite, because if X is a finite set, it considers with the but when it is whenever it is an infinite set, it becomes it's of interest and finite complement topology. But when X is finite, when it is finite, then it actually coincides with the discrete topology. With which every subset is open. In the case of discrete topology, but in the case of in that case, if X is finite, actually we get that you can see that it coincides with the topology, the discrete topology, and in that discrete topology we have seen that every subset is open in the case of discrete topology. Now we are going to define closed sets. See, how can we define closed sets in a topological space? So initially you think that a non-empty set together with a topology is defined, and that's X and the tau is the topology. So X together tau is the topological space. In this space we say that C is a closed set. See, let C be a subset of X. A subset C of the topological space X is taken, and we say that it is closed. For that, you have to take the complement, so that is C complement. C complement is equal to X minus C. See, consider C complement equal to X minus C. If this C complement is open, only if a C complement is open, then we say that C is closed. So if C is closed, if and only if X minus C is open. Okay, next we have the definition. We define the limit point. We have to define limit point and the cluster point, or limit point or cluster point or accumulation point. All the three are the same concept, but different words are used to, different names are used to represent the same concept, the limit point. How do we define the limit point? Limit point or accumulation point of a subset A of a topological space. We consider a topological space X tau, and let A be a subset of X, A be a subset of the topological space, and we say that, or we can define that X is a member small x. We take an element X of the underlying space, a capital X an element of X. It's a limit point of A. It's a limit point of A if every open set if every open set which contains x contains an element of a other than x. So that is the condition. See, if we see that every open set which contains x, and that's open, it's an open set of open subset of x, capital X. See, if every open set of capital X which contains x contains some point of if it contains some point of capital A, some point of the subset A other than x. If it contains some point of A other than x, then we say that that point x is a limit point of A. You may note that if a point which is a limit point of A may or may not be present in A. See, if a point is an integral point of A, then it is a limit point of A. Then it is present in it's clearly present in A. But if a point which is on the boundary of the set A, there are some points which lay on the boundary of the set A, then it cannot. It is then if it is not actually if it is not included, if it is not already given that it is in that if the boundary is inside that inside the given set A, then we can say that it is not inside that limit point is not in A, it is then outside A. So in some situation this boundary or a part of either entirely the boundary or a part of the boundary may be outside the given set A. The boundary of A, that means a boundary of A may not be always present inside in A. In such situation, that limit point may be it may be outside A. Thus, too, with respect to the limit points, with respect to the, when there exists a limit point, then two situations may happen. The first situation, that limit point is a member of A, can be a member of A. The limit point can be a member of A. In the second situation, it cannot be a member of A. Thus, we have two situations. And you know, A set may contain more than one limit point. See, a collection of or infinite in some situation there exists infinitely many limit points for a set. So it is now meaningful to consider the set of all limit points of a set. So it is now we are now going to define such a set. The set of all limit point, we define the set of all limit points of a set of a given set A, and that set is called the derived set of A, and it is called it is the derived set of A is denoted by A prime. So A dash, we use the notation A dash to denote A prime or A dash to denote the set of all limit points of A. So what is meant by a derived set? The derived set is the set of all limit points of a given set A. It is called the derived set of A. Then we now try to answer a question. A question is given. Consider the topological space R top prime, where top prime is a topology. That topology is the finite complement topology. Here top prime is the finite complement topology. So consider the topological space R top prime, where top prime is the finite complement topology. Then the question is that this is the statement. The question is that when A is any infinite set, let A be a given infinite set, then find its derived set. So in this question we try to find the derived set of a subset of a derived set of a subset of a topological space. That topological space is R T prime, R top prime, and then top prime. But here top prime is the contains all open sets in the finite complement topology. Here, since we want to find the derived set of A, see that must contain all limit points of A. So the derived set of A must contain all limit points of A. Therefore, we want to obtain all limit points of A. So for that, let's. But where should we search for these limit points? Since A is a subset of the mother set capital R, see the set of real numbers. Since A is a subset of real numbers, it's not it's not possible to search for the limit point of A outside R. See, so we can search. We can search for the limit points of the set A only inside R, only in R. Therefore, we arbitrarily assume that X is a limit point of R. See, let's consider a member of R. That means a real number. So let X be a member of R. That means X is an element of R. And when X is an element of R and an open set O is taken, let us take an open set O containing contained in an open set O which is contained in X, not containing X is equal to R actually, and we choose an open set O which is contained in X. That means in R. R is the mother set, and also that contains small x. It contains the taken open set must contain the element of R, the arbitrarily chosen element, or the real number. Small x is any real number, and O is chosen such that O is a subset of R, and X is a member of O. X is a member of O. That means X is an element of O. But according to definition of the finite complement topology, since O is a member of the top prime, top prime, or R minus O, what about R minus O? The nature of R minus O is that it is finite. So R minus O must be finite. R minus O is finite, and you can take together the two sets O, and the first set is O, the open set O, and its complement O complement equal to R minus O. We consider so together O and R minus O. See, all real numbers are divided into two classes, into two sets. The real numbers, a set of real numbers which belong to R minus O. There are real numbers which belong to R minus O, and there exist remaining real numbers. All the remaining real numbers must belong to O. And now again we think about the infinite set A. We consider the infinite set A, and that contains infinitely many elements. And since A is a subset of R, then there exists when we think about the elements of A, for a member of A. Suppose small a is a member of A, then it can be either in O or in R minus O, not in both, because they are disjoint. These two sets are disjoint. So any member of A must be any member of capital A must be a member of O or a member of R minus O, and not both together. Both situation cannot happen together. So and also we know that R minus O is finite. Since R minus O is already, we know that R minus O is finite from the definition. R minus O is finite, but A contains infinitely many points. A contains. So only finitely many points of A must go to R minus O, and the remaining, that means infinitely many points. The remaining elements, or infinitely many points are there remaining. The remaining elements must be present in O. It must go to O. And so therefore we can think about the open set, and since this open set O is taken such that it contains a small x, so the taken open set O contains small x, and also O contains infinitely many points of A. And therefore it is clear that O contains at least or some point of A, because O contains infinitely many points of A, and therefore we can say that O contains some point of A other than X. Clearly, it is very clear that O contains the open set O, arbitrarily chosen open set O contains infinitely many. Actually, it contains infinitely many points other than X. So we can say that it contains some points, at least some points other than X. and therefore this says that, so this fact leads to the conclusion that x, the element small x is a limit point of O. Therefore x must be present in the derived set of O, that is A prime. Since this is true for every real number chosen from R, see, we have chosen small x as an arbitrary element of capital R. So this can happen. The same arguments, all these steps, above steps will be true. It will follow. All those steps will follow without any question. It follow in the case of every real number chosen, arbitrarily real number chosen from R. Therefore, we can say that every real number is a limit point of the set A, and therefore the derived set of A is equal to R. And that's the end of that question. I am going to conclude this video here. Thank you.